Hi everyone, thank you for attending my session. Today, I'd like to talk about our POC for TiDB process and tuning details. Title, Kaizen, Mercari's method for tuning TiDB. First, let me introduce myself. I'm Takashi Honda, worked at Mercari as DBRE. DBRE team has a responsibility for data store used by Mercari groups. This is an agenda for today's session. First, I'd like to talk about the background, why we started to use TiDB, and next I'll talk about performance tests and tunings. And you may have already known about TiDB latency issues, which is larger than MySQL, so I want to talk how we measure the impact for it. Finally, I summarize this session. First, about the background. Before that, I'd like to explain about Mercari. The mission of Mercari Group is circulate all forms of value to unleash the potential in all people. To achieve this mission, we serve many platforms such as marketplace, financial, cryptocurrency, and spot jobs. Today's session is for marketplace. The service name is Mercari. Mercari is a C2C marketplace. Everyone can buy and sell everything what you don't need anymore. The service details are described the right side. The number of customers and number of items are the largest in Japanese C2C marketplace services. Mercari service uses huge MySQL as the backend, and its MySQL is one of our coverages. Let's talk about our huge MySQL issues. These are features of Mercari MySQL servers. The total size is over 40 terabytes, and there are over 50 servers. In addition to this, they are not on cloud, but for on-premise. There are some operational issues caused by those features. I'll explain about them by three topics: development and scalability and elasticity. Our MySQLs implemented vertical sharding, but not horizontal because of service features. All of customers can buy items from anywhere and sell. So it's difficult to introduce horizontal sharding simply because of cross transactions. About development, the vertical sharding unit is not linked with application logic, so it makes developers harder to develop new features. They should be aware table and shard mappings. Also, join table cross shard is not allowed. About scaling, it's due to on-premise as you think. Also, elasticity, since the data size is too large, it takes about 1.5 days to launch new instances. It couldn't enforce raising traffic suddenly. You may think we should migrate the public cloud, such as RDB or RDS or CloudScale, but it couldn't, because our service resources are too large, so there are few types to satisfy our demand, or it will reach the limit for a few years. Therefore, migrating to manage the MySQL server are not fundamental solutions. Under those situations, migrating TiDB Cloud is one of the fundamental solutions for us. The reason why TiDB was able to be candidate is solving elasticity and scalability. The speed of scaling is so faster than our current launching time, and later can be scaled out, so it will solve our scaling and elasticity problems. Also, high compatibility with MySQL was enchanting for us. It means back-end developers don't need to change their code, not so many. Furthermore, no capacity limitations are important points. Those points follow service growth more. In addition to that, migrating to cloud service will give us some benefits than managing data center. For example, security risks are requiring special skills. In particular, those skills are too rare and it's difficult to hire. The TiDB Cloud is one of the candidate migration targets, so we decided to have POC on TiDB Cloud. The objective of POC is TiDB Cloud works for Mercari's workload. From the next, I'll explain how we had POC in detail. Let's go to the performance test section. First, I describe how we did performance tests. In our case, it's difficult or impossible to simulate all of traffic or queries on production environment because our system has many microservices, so it's difficult to create test environment. Also, there are some queries executed at specific time, like batch job or special scheduled events and so on. So we have decided to create original test scenario by ourselves. It's impossible to simulate all queries executed production completely, so we used representative queries. These are 40 points to pick up queries. First, select queries for low latency but execute many times. Second, select queries high latency but executed rarely. Third point, all book queries have transactions, so even though select query. Fourth, pick up one shard, which is the most important for us. The queries picked with such points are not enough for our current QPS, so we used Sysbench's implemented scenario to satisfy actual QPS. In other words, we combined Sysbench's scenario and our original test scenarios. And creating test spec in that way, and we decided performance tests objective to 1.5 million QPS. This value is predicted value of near future based on our GMV and current QPS. And we can achieve that value. I'll share about QPS achieved at all. From this slide, I'll explain what tuning we did for the test, and this section is main of my presentation. First, about clustered index or non-clustered index. The difference between these indexes are how TiDB access to raw data. Clustered is mapped directly PK and value, but also non-clustered has intermediate ID, which is called TiDB raw ID. And TiDB raw ID is generated by TiDB internally, so PK is mapped to TiDB raw ID and TiDB raw ID to raw data. As you can see these differences, clustered index has benefit for high throughput because it can access raw value directly. But it weaks the possibility causing hotspot. Non-clustered is opposite of clustered, resist to hotspot, but throughput is lower because there are two steps to access value. Which index should we use? PinchUp suggests if the number of auto increment is less than 30,000 QPS for each table, clustered is enough. Also, if it over 30,000 QPS, we should adopt non-clustered. At first, we used non-clustered for all of tables because afraid of hotspot issue. However, this index difference had a large impact on throughput, and auto-increment QPS is not so high as 30,000 QPS in all tables, so we introduced clustered index for all tables. Next, about follower read. We expected follower read function is that TiKB follower node can execute read queries without talking with TiKB reader, and it is rising throughput at the result. However, the actual behavior is different from our thoughts. It is meaningful only when TiKB has latest data. The flow of follower read is like this. First, follower request read index to reader to confirm follower has latest data. If follower doesn't have latest one, follower waits to sync latest data from reader. Also, if follower has latest, follower executes query and returns data. This function is useful when the reader is high load because of hotspot issue and the data isn't updated much time. We didn't use this function because we didn't face hotspot and the Load was evenly balanced in our workload. And load by read index wasn't a problem. Other tips, you can configure to specify the follower by TiDB replica read parameter. You can choose which follower, you can choose the follower, randomize or load balancing or same zone and etc. Next, about stale read. Stale read is a function to allow TiDB returns a value of historical versions. So all of follower can serve read queries. To enable this function, we should confirm the service characteristic whether it's acceptable to fetch historical data. This function is effective for performance improvement in such situations. TiDB3 copy latency is high, or latency of read index request, as mentioned above, was high because follower can return the data without talking with reader, even if follower has the historic version value. We didn't enable this function because both 3 copy and read index issue hasn't been shown in our workload. Next, about cache. The plan cache is a function to cache query planning, which is used to prepare and execute. This cache are stored each TiDB node, and they aren't shared with each other node. Note that there are some conditions to available plan cache. These are examples. First, query uses sequence like select or update, general sequence, and second, not contains non-correlated subquery like this. And query doesn't use partition or temp table, and query's limit condition is lower than 10,000, and there are another conditions. In our test, we use TiDB 7.1, but plan cache isn't available for point-to-get queries. Point-to-get is the largest number query in our workload. However, PinTap gave us a patch to enable plan cache for point-to-get, and the performance has been improved thanks in this cache. Next, Copro cache. Copro cache is a cache of push-down calculated result for each TiDB node. To say short, it caches the result calculated at TiKB on TiDB node. This cache is aimed to return only result from TiDB without accessing TiKB. And complex calculation like aggregation should be done at TiKB instead of TiDB. This cache is valid only when push-down request. It means query context are completely same. Also, this cache unit is the regions. In other words, if region would be updated, then the cache will be marked as invalid. So it's not effective when the region is updated frequently. In our code, there are a lot of point-to-get and batch point-to-get queries, but Copro cache is not available for such queries, so we didn't use this cache. Next, about PD. TiDB enabled TSO follower proxy allows the TSO timestamp workflow request not only PD reader, but also PD follower. In our workload, all of queries are executed with transactions as above I mentioned, so we expected this parameter would improve throughput by reducing TSO latency. But in fact, PD reader didn't exceed the limit. Rather than the overhead, because of enabling this parameter had a negative impact. Why? As a premise, TSO issued by PD reader only, so when PD follower receives TSO, it proceeds to PD reader. Not using proxy, all of TSO goes to PD reader, but enabling proxy will follower receive TSO and proceed to reader. This proxy's request response was overhead for us, so we didn't use this function. Next, TiDB throw log threshold. This parameter is threshold to out throw log. It's same with long query time with MySQL. During the test, the amount of traffic was so huge and we got so many throw logs, so we tried to reduce load by these logs. It was effective to open page of diagnosis on TiDB Cloud console. It became faster both to show and filter the result, but not good for TiDB spot throughput. From this, I introduced some parameters related with gRPC on TiDB. First, max batch wait time. It is a timeout to request from TiDB to TiKB. When set this parameter, the request will be waited and sent batch request. The approach is that to reduce the request to TiKB from TiDB and improve the throughput, sacrificing some latencies. Since in our workload, there are many lightweight queries, we try to reduce the communication times between TiDB and TiKB. And this parameter was effective by combined with gRPC connection count. The gRPC connection count is a limit of gRPC connection between TiDB and TiKB. In 1.5 million QPS load, the request to TiKB has been distributed because there are many TiDB nodes. So only max batch wait time wasn't enough for us. As we could reduce connection count by reducing the number of gRPC connection count and increasing max batch wait time, the throughput has been improved. When the number of TiDB and TiKB were very large, these gRPC connection count and max batch wait time combination was effective. And next, gRPC concurrency is the number of gRPC worker threads. Our workload is RAID heavy. It means there are much select queries than insert, update, delete. By increasing this concurrency, we expected improving overall throughput to handle numerous read queries in parallel. Through those CPU usage of TiKB was increased as a side effect, but the throughput had been improved by this parameter. Next, store I/O pool size. It is the number of threads TiKB writes logsdb. Equals 0, default case, last store thread flushes logs to disk logsdb immediately. Also, larger than 0 case, last store thread flushes to store writer thread once, and the thread flushes to logsdb after number of logs a certain number. We tried to use this parameter to reduce the latency of commit log duration by updating queries, but it wasn't effective for our read-heavy workload, so it didn't contribute in improving write throughput, even though updating query were improved. That's all of my trainings. To summarize our changes and results like this. Front cache and clustered index are very effective for our workload, but also thread parameters like max batch wait time or gRPC concurrency pool size was a bit. How was the number of servers? It was like this. TiDB nodes are over 100, TiKB are over 80. Surprisingly, PD was enough for only 3 nodes, even though our workload creates TSO on each queries. Finally, our QPS was over 3 million QPS. It was about 2 times of our queries. Unofficially, it over 4.5 million. Next, latency issues. As you know, the latency of TiDB is slower than MySQL in general. It's due to the architecture of TiDB. So we should consider the increase of latency is acceptable for us before migration. I introduced the method how and what we did it to measure the impact of latency. First, we use the same parameters when achieve the throughput object because it's no worse. We can't achieve the object of throughput even if latency is small. We should evaluate both latency and throughput. And additional latency is measured 2 patterns, best and normal normal load. Best is thread equality in sysbench parameter, and normal is CPU utilization about 30 or 50%. Note that in our POC environment, the network latency, TTL or TiDB Cloud, was higher than MySQL 1. It's not to be able to be ignored. MySQL is smaller than 1 millisec, about 0.x millisec, but TiDB takes about 3 or 4 millisec. The latency result for each query type is like this. The object values are based on our GSLO. As you can see from this graph, MySQL is quite slower. MySQL is quite faster, but TiDB is slower than if its load is if load is low, even though including TTL. Under high load situation, they are too slower than now. To summarize that graph, it's about 1.5 or 10 times slower than our current MySQL. To summarize easily, it seems to be expected about 50% slowdown than current MySQL in general cases. This 50% slowdown is acceptable for us. How impact for our service? No one doesn't have that answer. So we confirmed it. We called it latency injection test. Let me share about latency injection test. As a name, we inject latency between MySQL servers and client on production environment directly. We couldn't use A/B test or performance test, so preparing test environment because the coverage of them are not trustworthy, but also to inject latency directly in production environment is the most trustful way. As I said before, no one doesn't have an answer how impact by injecting latency. So we should create an architecture to revert as soon as possible. Considering those conditions, we decided to use ProxySQL in front of MySQL servers. To figure out the application architecture, this is a simple graph client MySQL servers. We injected ProxySQL servers in front of each endpoint, write and read by changing DNS name. I want to go into detail here, but we have some countermeasures to follow the server down. For example, ProxySQL writers follow the failover of MySQL primary by switching automatically in a short time. We set delay at each ProxySQL server so we can simulate the situation query slow down from the view of client side. Why we use ProxySQL? There are some reasons. First, compatibility with MySQL protocol. So we don't need to change anything on client side. We can set some session variable by init connect. It helps inserting ProxySQL without any application errors. Secondly, we can insert rollback latency setting by changing the default query delay parameter. We can roll back latency in about 1 second when we found there are some issues on production environment, and we can inject latency gradually by make some ProxySQL changing parameters. Other ideas are little hard to implement using TC command on MySQL server or do a script with HA proxy. The most simplest way is introducing ProxySQL. Also, it's very easy to scale out ProxySQL servers. In the last of test, about 1,000 VPCU are required only for ProxySQL servers. The result of our test is following. There was no large impact for customer. GMV or customer inquiries are not changed so much in, in spite of inserting PostgreSQL and adding middle-level latency. But there was some points to have to be fixed. They are very simple but important, like N+1 queries and inefficient query, exhausted TiDB connection pool, or redundant operations, etc. By this test, we can clarify the impact latency increasing and plan the next step to fix. The important point is that this test has done in production environment without any announcement for customers. We can simulate the situation after migration, and we can measure the impact delay. I think doing in production environment is the most important point in this test. Let me summarize my presentation. We had some issues for huge MySQL servers. To solve those issues, we started POC for TiDB Cloud. The point is whether TiDB Cloud works for Mercari's workload. During the POC, we had some performance tunings, and the tuning points are this. By those tunings and those such resources, though our objective QPS was 1.5 million bats, we achieved over 3 million QPS. Also, another problem is low to how handle 50% slowdown latency. To confirm the impact, we had latency injection testing on production environment. Injecting PostgreSQL between client and MySQL servers and add latency on PostgreSQL servers. By injecting latency on production environment without any announcement for customers, we can simulate the situation after TiDB migration and clarify to current issues. In particular throughput test, PinCap gave us a big support to achieve our objectives. Thanks for all the members for this project. Let me describe our current future works. From those tests, we have decided to migrate our MySQL to TiDB Cloud. Now we are going migration for each vertical shard into each TiDB cluster. There are also future development plans for that. After migration has completed, we are going to consolidate TiDB cluster into one cluster to reduce operation costs. If you have interested in our migration project, and if you want to handle DB servers, which is large traffic and data responsibility with business impact, please feel free to apply our careers. We want to work with you. And that's all of my session. If you have any questions for me for this session, feel free to ask me. I'll be in this venue. Thank you all.